In the hush of a quiet night, your mind begins to wander far to places where the stone seems soft, and solid things can slip through bars. Come close and listen deep inside. The universe is whispering. Close your eyes if you like, and breathe softly. Feel the weight of your body sinking gently into the surface beneath you. The world around, quiet and still. Yet even as everything seems peaceful, something extraordinary is stirring, not outside, but deep within the very fabric of the universe itself. Tonight, you and I will take a slow, careful journey together to that hidden place, a realm so small that the everyday rules you know seem to flip and shimmer. You know the world as solid and steady. A dropped book falls to the floor. A flame gives off warmth and light. The stars twinkle far away in steadiness. But if you could shrink down far beyond what your eyes can see to the tiniest corners inside the matter that makes you and me, the story changes. Here, in the whisper-soft shadows of existence, certainty becomes mystery, and mystery becomes a gentle dance. In the early years of the last century, curious explorers of nature began to peer more closely than ever before, not with adventure hats or telescopes aimed at distant stars, but with instruments and ideas that could see the very building blocks of everything, the bits of matter smaller than atoms, smaller than light itself. What they found was strange and beautiful. Light, the very stuff that lets you see, had secrets of its own. It seemed to flow and ripple like waves on a pond, spreading out gracefully, bending and weaving around corners. But sometimes, the same light behaved not like waves, but like tiny particles, little packets of energy that traveled in straight lines. How could something be both? Could the universe really play tricks so quietly and so deeply? The answer came, softly at first, from a man named Max Planck. He was not the sort to rush into wild ideas. Instead, he was careful, thoughtful, the kind of thinker who listens to the music inside math and lets it reveal its story. Planck faced a puzzle. When objects are heated, they glow. Heat a metal spoon till it shines red, then orange, then white-hot. This glow gives off energy in waves of light, but the old math predicted an impossible flood that should be infinite energy that cannot be. Planck's insight was gentle, like a quiet ripple on a still lake in the dark. What if energy, instead of flowing endlessly in smooth waves, came in tiny unbreakable packets, little steps, not a smooth climb? Quanta. Think of energy like coins in your pocket. You can't have half a penny. Energy comes in full coins only, each one tied to the rhythm of the light's color and frequency. This idea fixed the math and opened the door to the most wondrous and strange world we are about to enter. The quantum world. Planck's idea did not shout, it whispered, and the universe listened. From that whisper, a new story began to unfold. One where particles like electrons could be here and there at the same time, where simply looking at something could change what it was, where the path from one moment to the next was woven from countless possibilities, rather than one predetermined thread. Imagine yourself standing at the edge of a vast ocean at night. The waves lap gently at your feet. But beneath the surface lies a realm you cannot see, a world of patterns and rhythms you've yet to understand. Quantum physics is like diving beneath those waves, exploring the quiet orders in the seeming chaos. It doesn't demand that you grasp every ripple or equation tonight. Instead, it invites you to wander gently, letting the currents guide you. What does it mean to be certain? To know where something is or what it is doing. You'll find that certainty is a luxury here. The quantum realm offers you a tapestry of maybes, a garden of possibilities. And as you drift through this garden with me, you'll discover that even the simplest question, what is light, what is matter, has answers that flutter softly between what we see and what we imagine. Tonight, your mind steps lightly at first. You are neither rushed nor burdened. Think of yourself as a calm traveler passing through mysterious forests lit by fireflies, or as a gentle dreamer drifting over mountains cloaked in twilight mist. Each step unearths a new marvel, a new poem written in particles and waves. And so, we begin. The world as you know it feels solid, predictable, and kind. But just beneath that kindness is a secret, a shimmering dance that beckons you to listen closely. In the chapters ahead, you will meet light, behaving like a wave, and a particle at the same time. You will see how observing the smallest things changes what they are. You will glimpse a world where walls can be passed through without breaking, and empty space is alive with unseen whisperings. For now, Remember this soft invitation to wander gently, to accept not knowing, and to float quietly in the dazzling mystery that is your universe. The night is deep, the stars are watching, and the quantum world awaits your quiet presence. Before we close this chapter, imagine a tiny beam of light, a single photon, traveling through the darkness. It moves like a ghost, both here and there, its path a shimmering cloud of possibilities. It doesn't decide where it will land until you look, until you listen, until you ask the question softly and give the universe permission to answer. And with that thought, rest your head and drift into sleep, into dreams, into a gentle journey that begins with a single spark of curiosity. Tomorrow, we will follow that photon further, into the strange dance where waves become particles and particles can be everywhere at once. If you were to ask what quantum physics is, you might say it is the art of listening to the whispers beneath the world's solid song. And now, your ears and your heart are ready. Sleep well, dear traveler. The stars and particles will be here when you wake. Light's secret dance, waves and particles between the veil. Close your eyes and breathe in deep. Feel light's soft footsteps on the street. Sometimes it ripples, sometimes it leaps. A dance of shadows, bold and sweet. A silent song that never ends. Wave meets particle, and light transcends. Imagine, just for a moment, that you're watching a quiet river in the evening light. The water flows smoothly, rippling gently over stones and around bends. This river is like a wave, spreading, overlapping, and dancing, sometimes splashing and shimmering. Now imagine a different world, a world where that same river could also behave like a tiny droplet, a particle of water, precise and alone, following a clear path. It sounds strange, doesn't it? Yet this is exactly how light behaves, the very thing that fills your world with color and warmth. You've known light since the first day you blinked awake. You see sunlight filtering through your window, the glow a welcome comfort. But science tells us that light is more mysterious and magical than eyes alone can grasp. For centuries, people thought of light as a wave, a ripple, spreading out in space, bending around corners, creating patterns of bright and dark bands when shining through two narrow slits. This wave idea explains rainbows, the colors arcing across a misty sky after rain, and the soft glow of a candle flickering in the dark. But early in the 20th century, something strange began to emerge. When light shines on certain metals, it causes tiny particles called electrons to jump free from the surface. People called this the photoelectric effect. At first, it seemed straightforward. Light hits the metal, gives energy, and electrons leap away. But experiments told a different tale. It wasn't the brightness of the light that mattered most, but its color or frequency. Only light above a certain frequency, even if faint, could shake electrons loose. This puzzled scientists because waves, according to the theories back then, should deliver energy based on their intensity, not their color. Then came a gentle but profound whisper in physics from none other than Albert Einstein. He proposed that light isn't just a wave, but also comes in little packets, particles of light called photons. Each photon carries a specific amount of energy tied to its frequency. If a photon has enough energy, it can knock an electron loose. If not, no number of photons, no matter how bright, can do the job. It's like having a handful of keys, but only the right one opens the door. This idea that light is both a wave and a particle might seem like trying to see the same spoon, as silver and transparent at the same time, but light plays by rules far from ordinary. Imagine the photons as dancers, sometimes waltzing in waves, together and flowing, and sometimes stepping sharply and alone, like particles on a floor. Which behavior dominates depends on how we choose to observe them. To see this dance in action, imagine a simple experiment. A flashlight shines through a piece of cardboard with two tiny slits. Catch the light on a screen behind, and you expect a pattern, right? Light, seen as a wave, creates an interference pattern, bands of brightness and darkness, formed by waves overlapping, reinforcing and cancelling each other out. It is beautiful and predictable. Now, turn the flashlight down until it pulses just one photon at a time. Single dancer stepping onto the stage. You might guess that each photon chooses one slit or the other and lands in two clusters, like tiny rubber balls, fired randomly. Instead, as photons arrive one by one, the interference pattern slowly reappears on the screen, as if each lone photon somehow goes through both slits at once, interfering with itself. This puzzle, gentle and strange, is at the heart of quantum mystery. How can one photon be in many places at once? How can it pass through both slits simultaneously, as if it were a wave spread thin, but then appear as a particle when it lands? What shifts when we place a detector to observe the path? The next surprise is even more subtle. As soon as you peek with a detector to see which slit the photon passes through, this beautiful interference pattern fades and vanishes. The photon suddenly behaves like a particle again, as if the very act of watching nudges light to pick a side. Is it magic? No, it's a fragile dance between knowledge and existence. The universe seems to blur, shimmering with possibility, until we ask a question and then the dance chooses a definite step. Imagine that now. The glowing dance hall is drawn in ghostly patterns of wave functions, mathematical clouds that describe all the places a particle might be and all the ways it might move. Until measured, the particle is not a point, but a ripple of possibility, a fog where every path is part of the dance. When observed, the wave function collapses, the mist condenses, and the particle is found here. Now, certain. This idea challenges everything we think we know about the real and the unreal, about what exists. It is like watching a cloud that becomes a raindrop the moment you look closely. Is the cloud only a cloud when unobserved? Does the raindrop exist only when caught in your hand? Such questions do not have simple half-sentences as answers. They invite you instead into a quiet wonder, a softness where certainty is replaced by rhyme and rhythm, where reality whispers in tones both definite and delicate. And so, dear listener, as you lie calm and safe, imagine yourself as both wave and particle, spread across possibilities, yet grounded in the gentle hush of now. Let your mind float freely in this shimmering dance. As this chapter closes, imagine that the light passing through those two tiny slits is still dancing somewhere beyond sight, still weaving its graceful patterns between wave and particle, and that you, too, are part of a cosmic dance, where seeing is itself a step in the dance. Tomorrow, we will meet the secret mathematics that guides this dance. An equation gentle as water, powerful as stars, will unwrap the whisper of the wave function and learn how probability paints the shapes of the very small. Slowly breathe in once more, feel the calm deepen, and rest. The universe is humming its silent song, and you are listening. The whisper of the wave function, Schrödinger's equation, and the garden of possibility. Imagine a soft murmur beneath the silence, a gentle pulse threading through the stillness, a whisper that tells where particles may be, not a point, but a cloud of endless possibility. At the heart of the strange quantum dance is one equation, quiet yet profound, that carries the secret language of the universe's tiniest players. This is Schrödinger's equation, introduced gently in 1926 by Erwin Schrödinger, a physicist who dreamed of describing the quantum world not as sharp dots bouncing like billiard balls, but as waves spreading, shifting, and flowing in a sea of possibility. You don't need to wrestle with Greek letters or complex symbols to feel the beauty of Schrödinger's idea. Instead, picture it as a mathematical whisperer, wave function, that tells us everything we can know about a tiny quantum system. It doesn't shout precise locations or paths. It offers a cloud of probabilities, a haze of maybe. Imagine standing blindfolded in a quiet room. Somewhere, a cat is hiding. You can't see it, hear it, or touch it, but you can throw small balls and listen intently for the sound they make when they hit. After many throws, you build a mental map. The cat is probably here, maybe there, less so over there. This mental map is your wave functioner, probabilistic guide to where the cat might be. In the quantum world, electrons are not tiny balls orbiting a nucleus like planets around a sun. Instead, their wave functions form soft clouds called orbitals where an electron is likely to be found. These clouds ripple gently, like patterns on a pond's surface disturbed by a breeze, and Schrödinger's equation describes how these gentle ripples evolve over time. What happens then when you take a measurement task? The particle, where are you? The cloud disappears, collapsing to a single point. The electron is found here, not somewhere else. Before measurement, the electron's position is a shimmering fog of possibility. After, it's a single tangible location. This wave-based view of reality is not only strange, it's deeply beautiful. It invites us to see the quantum world not as cold, hard, and mechanical, but fluid, uncertain, and alive with potential. But this gentle uncertainty carries a deeper mystery. How can a particle's position be uncertain? How does nature draw the line between possibility and reality? Schrödinger's equation allows the wave function to evolve, deterministically smoothly flowing as time passes. Yet, when the wave function collapses during measurement, the outcome seems sudden, abrupt, and probabilistic. This divide gave rise to a famous philosophical challenge known as Schrödinger's cat imagined creature caught between life and death in a sealed box. The cat's fate isn't fixed until we open the box and look, mirroring the mysterious collapse of the wave function. Schrödinger himself introduced this thought experiment to show how absurd it seemed to apply quantum superpositions to everyday objects. As you ponder this, think also of Heisenberg's uncertainty principle, a companion to Schrödinger's equation. It tells us that certain pairs of properties like position and momentum cannot both be precisely known at the same time. The more you know one, the less you know the other. This is not an artifact of measuring instruments, but a fundamental feature of the quantum realm. Imagine trying to catch a wisp of mist in your hands. The tighter you squeeze, the more the mist slips away. This principle is woven into the fabric of the universe, providing a natural fuzziness and preventing electrons from collapsing into their nucleus. This delicate balance is why atoms are stable, why chemistry is rich, and why the world you see is steadfast and solid. The wave function, Schrödinger's gentle cloud, beautifully describes the quantum probabilities but remains a whisper, intangible and elusive. Is it just a tool for calculation and expression of what we know? Or is it something physically real, a ghostly veil draped over reality until lifted by observation? The answer is one of the grand questions quantum physics still invites us to ask. In the quiet rooms of physics, some embrace the wave function as a symbol of knowledge. Others believe it's a fundamental part of the universe's deep tapestry. Schrödinger's equation does not demand an answer, only encourages exploration. So, as you rest, let this idea settle softly, that beneath the solid world, beneath the certainty of reason, lies a garden of shimmering possibilities, where nothing is pinned down until it chooses to be. Reality is not a fixed photograph, but a living painting, ever moving, shaped by the act of looking. Tomorrow, we'll tiptoe further into that garden, exploring how particles defy walls and barriers, slipping through to the other side when logic says they cannot. We'll meet the mysterious phenomenon of quantum tunneling, a secret shortcut through the fabric of reality. For now, breathe deeply. Feel yourself part of this unfolding mystery, a ripple in the vast quantum ocean, where the very small teaches the very large about uncertainty, grace, and chance. Quantum tunneling. When particles take the hidden path, imagine you're standing in a quiet room, facing a solid wall. You toss a tennis ball gently at the wall. It bounces back reliably, obeying the classical laws of physics. The wall is a firm boundary, impassable, absolute. But in the strange, tiny world of quantum physics, particles like electrons or photons sometimes behave quite differently. In the quantum realm, predictability takes a holiday. A particle traveling toward a barrier that looks solid and impenetrable can actually slip through it and appear on the other side, even though it seemingly doesn't have enough energy to cross it. It's as if the particle takes a secret shortcut, a hidden path through the barrier itself. This remarkable and baffling phenomenon is known as quantum tunneling. How can this be? To understand, we need to revisit the concept of the wave function, that ghostly cloud of probabilities described by Schrödinger's equation. Instead of being a pinpoint particle traveling in a line, the quantum particle's wave function spreads out like a ripple in a pond, gradually fading but never abruptly stopping. When the particle encounters a barrier, say, a region of space, where it would not classically have enough energy to go over, the wave function doesn't just vanish. Instead, it tapers off, whispers through the barrier, and if the barrier is thin or low enough, a faint ghost of the wave can reach the other side. Because the wave function represents the probability of finding the particle, this means there is a small but real chance the particle might be detected beyond the barrier. This is not magic, it is math, quantum math, and it has been experimentally verified again and again. Real-world examples of tunneling, some of the most vital processes in the universe rely on this quantum shortcut. Radioactive decay, nuclei of unstable atoms, eject particles like alpha particles, even though classical physics says they should be trapped forever. It's quantum tunneling that allows these particles to escape, making radioactive decay possible. Nuclear fusion in stars. The Sun and other stars shine because hydrogen nuclei fuse to form helium. Classically, the positively charged protons should repel each other strongly and never fuse at the observed rates. Yet quantum tunneling lets protons penetrate the repulsive barrier and fuse, powering the stellar furnaces. Scanning tunneling microscope (STM). On Earth, scientists use tunneling. In technology, the STM can image surfaces with atomic precision by detecting the tiny tunneling current of electrons crossing the small gap between a sharp tip and the surface, mapping the landscape of atoms without touching them. Tunneling also underlies certain electronic components like tunnel diodes and quantum dots, crucial for modern technology. As engineers miniaturize circuits, quantum tunneling becomes a double-edged sword. It can cause unwanted currents, but also opens doors to new quantum technologies. The deeper lesson of tunneling. Quantum tunneling teaches us something profound about reality. The world isn't made of rigid walls and unbreakable boundaries. Instead, it's a shimmering tapestry woven from probabilities. Barriers are no longer absolute, they are suggestions, places where particles might hesitate but not always stop. The tennis ball still bounces, the table still stands firm, but at the scale of the very small, particles can and do take the shortcut through the wall, surprising us with their secret paths. Imagine you have a pair of gloves, one left hand, one right hand. You place each into two separate boxes and send them to opposite sides of the world. When you open one box and find a left glove, you instantly know the other must be the right glove, even without looking. The gloves had their identities all along. This makes perfect logical sense, but quantum entanglement is far weirder. Entangled particles don't have their properties fixed before measurement. It's as if the gloves don't decide which hand they are until the moment you open one box, and finding the left glove immediately tells the other to be the right, even if that second box is light years away. How entanglement happens. Particles become entangled through interactions, like being born together in the same event, colliding, or otherwise linking their quantum states. Once entangled, their quantum states are no longer independent. They form a shared identity described by a single joint wave function. What makes entanglement truly mind-bending is this: measuring one particle immediately affects the state of its partner, no matter the distance separating them. If you measure the spin of one particle and get up, the other's spin will instantly be down. This correlation happens every time you measure them, perfectly coordinated and faster than any signal could travel, even faster than light. Albert Einstein famously called this spooky action at a distance, a phrase that captures the profound discomfort entanglement caused him. It seemed to violate a fundamental rule of physics, locality, the idea that objects are only influenced by their immediate surroundings and nothing can travel faster than the speed of light. Yet, experiments repeatedly confirm the spooky reality. Experiments and Bell's theorem. For decades, physicists debated whether entanglement demonstrated a flaw in quantum mechanics. Maybe some hidden variables secretly predetermined particle states, preserving locality and realism. The idea that objects have defined properties whether or not we measure them. In the 1960s, physicist John Bell provided a way to test this debate. Mathematically, Bell's theorem, it showed that if local hidden variables existed, particles would obey certain statistical inequalities. But if quantum mechanics was right, those inequalities could be violated. Experiments, starting with those of Alling aspect in the 1980s and many more since, display clear violations of Bell's inequalities. This means nature simply doesn't obey local realism. Either influences travel faster than light, or reality is fundamentally non-local in ways we don't fully understand. The verdict is solid: entanglement is real, and the universe is stranger than classical intuition allows. What entanglement means for reality? What exactly does this non-local connection mean? Interpretations vary dramatically, and physicists disagree. Some say entanglement shows that information is the currency of reality, more fundamental than matter or energy. Until measured, reality is a network of correlations, not isolated objects. Others believe in a deep non-local fabric of space-time. Entanglement might hint that space itself is an emergent phenomenon, woven from quantum connections between particles. In some bold theories, these connections form the very scaffolding of the universe. Then there are interpretations like the many worlds interpretation, where measurement splits the universe into branches entangled with each other, but no longer interacting, avoiding spooky faster than light, influenced by allowing all possibilities to coexist separately. Others propose novel physics, beyond current quantum theory, to explain entanglement with new hidden variables or objective collapse mechanisms, still active areas of research. Despite the mystery, entanglement already fuels real-world technologies. It is the basis for quantum teleportation, the transfer of a quantum state from one particle to another at a distance. It underpins quantum cryptography, offering theoretically unbreakable security, since any eavesdropping disrupts entanglement and is instantly detected. Entanglement and everyday life, though entanglement plays out at microscopic scales, it is not confined there. Quantum particles are constantly interacting, creating vast webs of entanglement throughout the universe. But why don't we notice it in everyday life? The answer lies partly in decoherence, the same phenomenon that turns the fuzzy quantum world into the sharp classical world we know. As explored in Chapter 4, decoherence spreads quantum information into the environment, making an entanglement extremely fragile and effectively hidden at large scales. Macroscopic objects like tables or cats rapidly lose any entanglement, so classical logic prevails. Still, physicists have found evidence that entanglement might play roles in biological processes, hinting at a quantum life hidden beneath the warm, wet world we experience. Some birds, for example, seem to use entangled electrons in their eyes to navigate Earth's magnetic field with astonishing precision. How nature maintains such delicate quantum states amidst biological noise is a hot frontier in research called QuantumBiology. The philosophical implications entanglement forces us to reconsider the very nature of reality, connection, and causality. It challenges the classical picture of objects as separate, independently existing entities. Instead, the quantum universe suggests a deeply interconnected whole, where parts define each other and outcomes arise from relationships rather than standalone properties. It's a universe of wholeness and participation. This resonates with philosophical and even spiritual ideas about unity and oneness, where boundaries between self and other blur. While physics remains cautious about metaphysical leaps, the implications stir wonder about our place in the cosmic dance. Wrapping up the quantum dance from tunneling through walls to entanglement across vast distances, quantum physics reveals a world that defies everyday intuition. Particles are no longer isolated billiard balls. They are ripples in fields, waves of possibility, threads in a universal web of connection. They jump, wink, and whisper secrets that challenge how we understand cause, effect, and separate existence. Yet quantum theory remains our best guide, supported by countless experiments and the foundation of powerful technologies. In the coming chapters, we will explore how these quantum threads weave into the larger fabric of physics and what they mean for the future of science and technology. But for now, breathe deeply in this strange and shimmering universe, a place where connection is instantaneous, certainty is tempered with possibility, and reality invites you to wonder. The symphony of fields, quantum field theory, and the standard model. As we wander further into the quantum universe, it becomes clear that particles, those tiny, fundamental bits of matter and light, are not the ultimate building blocks of reality. Instead, we find ourselves entering a deeper realm, the realm of fields. Imagine the universe not as a collection of tiny billiard balls bumping into each other, but as an infinite ocean of rippling fields, each vibrating with possibility. This is the heart of quantum field theory, or QFT, the grand framework where particles emerge as excitations or ripples in these underlying fields. What is a field? Before quantum mechanics, physicists understood fields in classical terms. Consider the electric field, an invisible influence filling space around charged particles, pushing and pulling on others. It's smooth, continuous, and everywhere. Drop a charged particle into this sea, and it responds to the field's pull. Fields connect distant objects and carry forces. Quantum field theory takes this further, blending the notions of particles and fields into one seamless picture. Every fundamental particle corresponds to its own quantum field stretched out across the cosmos. When these fields vibrate in just the right way, a particle appears. Think of plucking a guitar string. The string itself is continuous, but the vibrations produce discrete musical notes. Similarly, localized excitations-based notes of the cosmic instrument become particles. Particles as field ripples take the electron. According to QFT, you're not gazing at a tiny ball whizzing around. Instead, you see a localized ripple in the electron field, extending everywhere yet concentrated in one spot. A photon isn't a bullet-like object, but a quantum of excitation. In the electromagnetic field, every known particle from quarks and neutrinos to the elusive Higgs boson is an excitation of its corresponding quantum field. This shift from particles to fields transforms our worldview. Reality is a symphony of invisible fields vibrating in harmony, weaving together everything we see and everything we can't. Particles appear as smallest, indivisible packets of these vibrational modes. The dance of creation, and a remarkable feature of QFT is its natural explanation for the creation and destruction of particles. High-energy collisions at places like the Large Hadron Collider don't pull particles out of thin air by magic. They shake the underlying fields so intensely that new ripples emerge, manifesting as particles. Conversely, particles can vanish, their energy reverting back into the field's hum. Antiparticles, such as the positron, the electron's antimatter counterpart, arise naturally as different modes of the same field, simply vibrating out of phase. When particles meet their antiparticles, they annihilate, sending energy back into ripples of the field, often as photons. The forces and their messengers. Quantum field theory also gives us a unified picture of the forces that govern particle interactions. Each fundamental force corresponds to its own field, and the carriers of these forces are particles themselves. Bosons ripples in these fields that mediate interactions. Electromagnetism is carried by photons, quanta of the electromagnetic field responsible for light and electric forces. The strong nuclear force, which binds quarks inside protons and neutrons, is mediated by gluons in the gluon field. The weak nuclear force, underpinning radioactive decay and nuclear fusion processes, involves the W and Z bosons. These force carriers aren't just messengers, they are dynamic players vibrating across their respective fields, enabling the universe's particles to push, pull, and transform. Enter the Higgs field, mass from the quantum C1. Of the crowning achievements of the quantum field framework is the discovery and understanding of the Higgs field and its associated particle, the Higgs boson. Before this insight, physicists puzzled over why particles have mass at all. The Higgs field pervades all space. Particles that interact strongly with it experience resistance, a kind of cosmic drag that manifests as mass. Picture swimming through molasses. The thicker the molasses, the harder it is to move, the heavier you feel. The Higgs field's molasses is why electrons, quarks and other particles have weight, and why the universe can form atoms and, eventually, in 2012. Experiments confirmed the Higgs boson's existence, cementing the standard model of particle physics as one of the most successful scientific theories ever. The Standard Model, a cosmic recipe. The Standard Model of particle physics is the quantum field theory's achievement writ large, a beautifully organized periodic table of particles and interactions that explains nearly all known phenomena except gravity. At its core, the Standard Model catalogues matter particles, quarks and leptons, arranged in 3 generations from lightest and most common to heavy and rare, force carriers, bosons, photons, gluons, W and Z, bosons, and the Higgs boson. This framework has withstood rigorous experimental tests, predicting particle properties, interaction strengths, and rare processes with uncanny accuracy. The precision is staggering. One prediction of the electron's magnetic moment matches experiments to more than 10 decimal places. The limitations and mysteries. Yet, the Standard Model is not the final story. It spectacularly excludes 2 cosmic biggies. Gravity, general relativity, governs the gravitational force, but integrating it consistently with quantum mechanics remains an open and profound challenge. Dark matter and dark energy. These mysterious substances make up most of the universe's mass energy budget, but leave no trace in the Standard Model's particle list. Physicists believe the Standard Model is a chapter in a deeper tale awaiting discovery, a theory that unites quantum mechanics, gravity, and cosmic mysteries, potentially through concepts like string theory or quantum gravity. Quantum fields all around. What does this mean for us? You yourself are a complex but beautiful pattern of excited quantum fields. Your body is not a mere assembly of tiny particles. It's a living orchestration of fields dancing in intricate harmony. Your thoughts, sensations, and even existence arise from waves and quanta humming beneath the surface of reality. These fields don't stop at the edge of your skin. They ripple outward, blending into the cosmic sea. There is no sharp boundary separating you from the universe. There are only varying patterns of excitation. Lessons from quantum field theory invites us to see the universe not as a static collection of parts, but as an ever-changing, interconnected symphony of possibility and actuality. Challenges us to move beyond images of particles as tiny billiard balls and embrace a reality woven from waves, vibrations, and continuous creation. It hints at fundamental unity beneath apparent diversity, and it offers tools of astonishing power with which to shape the future. Through particle colliders probing the smallest scales or quantum computers harnessing subtle quantum effects. Looking ahead as our journey continues, the dance of quantum fields leads us toward the frontiers of knowledge, where gravity and quantum mechanics seek unification, where quantum information reshapes computation, and where the strange rules of the quantum world inspire new technology, a new philosophy. For now, rest in the wonder that you, me, and the stars themselves are but ripples on an endless quantum ocean live with energy, resonating with possibility, and inviting us all to keep exploring. From mystery to masterpiece, solving the quantum puzzle of light and electron zine, the early 20th century, physicists understood that electrons could emit and absorb light, that charged particles interacted with electromagnetic fields, but the mathematics underlying these processes was fraught with confounding calculations simply exploded into nonsense. Energy values soared to infinity, where they should have remained finite and measurable. This problem was not merely technical, but foundational. If the equations told impossible stories, could they truly describe nature? Enter a group of brilliant physicists: Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, who found a way to tame the wild infinities. Their approach, known as renormalization, cleansed the math, rendering QED not just coherent, but astonishingly accurate. Among them, Richard Feynman stands out not just for his mathematical prowess, but for turning abstract quantum interactions into vivid visual stories. He introduced what we now call Feynman diagrams, simple, almost childlike sketches that depict how particles such as electrons and photons interact, emit, absorb, and dance around each other in a busy cosmic ballroom. Language of interactions. Feynman diagrams imagine time flowing from left to right across a page. A straight line might represent an electron traveling through space and time. A wavy line crossing it depicts a photon, the particle of light whizzing away or towards the electron. Sometimes the photon might split into other particles, or electrons might loop back and affect themselves. Every twist and turn stands for a mathematically quantifiable possibility. Unlike classical physics, where a particle takes a single, defined path, QED insists that every possible path contributes to the final outcome. You don't just consider the simplest way an electron emits a photon, you add up the influence of all conceivable ways, including the wildest detours and loops. This is not guesswork. The resulting interference of all paths produces probabilities that match experimental measurements with breathtaking precision. Triumph of precision. Predicting the electron's magnetic moment. One of QED's crowning achievements lies in explaining the anomalous magnetic moment of the electron. In classical terms, the electron is like a tiny bar magnet with a magnetic field of fixed strength, but experiments revealed subtle deviations, teeny tweaks, that classical physics couldn't explain. QED calculates these effects with stunning accuracy, matching the experimental results to over 10 decimal places. To put that in perspective, it's like measuring the distance across North America to within a fraction of a millimeter and getting it right. Beyond magnetic moments, QED elegantly describes phenomena such as Compton scattering, photons bouncing off electrons, shifting wavelength, bremsstrahlung, radiation emitted when it charged, particle slows down, pair production, light materializing into matter and antimatter particles. These processes, which sound like science fiction spells, unfold naturally in the mathematics of QED, the quantum dance. Particles as waves, waves as particles. Electrons and photons aren't tiny billiard balls moving they're ripples, vibrating fields spread across space. QED QED builds on this by seeing particles as excited ripples in their respective quantum fields. An electron is a localized excitation of the electron field, a photon, a ripple in the electromagnetic field, and so on. Forces themselves, like electromagnetism, arise from exchanges of these ripples photons, acting as messengers passed between charged particles. This field-centric view resolves paradoxes raised by particle-wave duality. Particles aren't fundamentally particles or waves. They're excitations of fields that can display wave-like or particle-like behavior, depending on the context. Challenges and limits QED's domain and beyond. While QED's success within the realm of electromagnetism is unparalleled, it doesn't claim to be a theory of everything. It excludes gravity altogether, which remains described by Einstein's classical general relativity, or at least, we don't yet have a fully reconciled quantum theory of gravity. Moreover, QED doesn't account for mysterious phenomena like dark matter or dark energy, which seem to govern the cosmos on large scales, but remain invisible and unexplained by the standard model of particle physics. So while QED dazzles on the small scale, the universe still holds secrets demanding new ideas. Simplicity beneath complexity, Feynman's guiding principle despite the complexity behind the calculations. Richard Feynman famously said the core rules of QED could fit on the back of a napkin. Particles take every possible path, each with a probability amplitude. You square the sum to find the actual probability. That's it. This deceptively simple statement encapsulates the quantum worldview. Particles don't trace a single trajectory from start to finish. Instead, all possible routes and interactions contribute in visible and invisible ways to the probability of any outcome. In this sense, reality is not a clockwork machine running on definite paths and fixed states, but a shimmering tapestry woven from probabilities and infinite possibilities. The road to new technologies. Why QED matters beyond the lab. QED's seeming abstraction has concrete impact. It underpins the very technology embedded in modern life. Semiconductors that power your phones, lasers that transmit information across continents, and nascent quantum computing experiments promising revolutionary computational power. Understanding the interplay of electrons and photons with such exquisite detail enables innovation and progress, turning quantum strangeness from a puzzling enigma into a realm of practical marvels. Looking ahead, from quantum electrodynamics to the unknown QED marks a pinnacle of human understanding of nature's fundamental processes, but also a doorway to future mysteries. It reveals how the universe's tiniest scales operate with astonishing subtlety and order, yet it invites humility. It may never be the final chapter. As physicist Richard Feynman cautioned, nature always has more up her sleeve. The quest continues for theories that weave gravity and quantum mechanics into a seamless whole, for glimpses into dark matter's nature, and for deeper insights into the quantum fabric of reality. In this chapter, we've traced the emergence of quantum electrodynamics as a vibrant, precise, and beautiful theory. It takes the intangible wave functions and probabilities of earlier chapters and gives them form, a cosmic dance of light and matter, choreographed by the rules that govern everything from the faint glow of stars to the glow of the lamp beside your bed. From the bizarre to the breathtaking, QED shows us that the universe is not only stranger than we imagine, it is stranger than we can imagine. Yet through persistence, creativity, and mathematical beauty, we glimpse the underlying rhythm of everything that is. Quantum physics has long been the realm of the incredibly small, electrons, photons, atoms, and particles dancing to the rhythm of probabilities and uncertainties. We've seen how these tiny building blocks behave in ways that defy intuition, being in multiple places at once, tunneling through barriers, and entangling across vast distances. Yet for decades, the domain of the living biology seemed altogether different. Life is messy, complex, warm, wet, and noisy. The molecular machines inside cells operate through countless random collisions and thermal vibrations. It's exactly this kind of environment that physicists assume to be hostile to delicate quantum effects, which tend to vanish quickly amid the chaos of warmth and noise. But what if life itself harnesses quantum mechanics? This is the bold and emerging field of quantum biology. It proposes that quantum phenomena are not confined to physics labs or particle accelerators, but may be quietly humming at the heart of multiple biological processes, perhaps shaping navigation, energy harvesting, sensing, and even smell, foraging. For north, quantum compass in birds considered a humble robin, a migratory bird that journeys thousands of miles every year with astonishing precision. How does it navigate? Scientists long suspected that birds possess an internal compass sensitive to the Earth's magnetic field. The unusual part, emerging evidence points to quantum entanglement at work in their eyes. Inside a bird's retina, a protein called krypton is thought to play a role. When sunlight excites this protein, it generates pairs of entangled electrons. These entangled spins are sensitive to the Earth's magnetic field, influencing the outcome of a chemical reaction. The bird's brain then uses this info to figure out direction. Initially met with skepticism, experiments have since offered modest but growing support. Remarkably, entanglement seems to persist long enough inside the noisy cellular environment to be biologically relevant, a feat that human engineers still struggle to achieve in artificial quantum devices. If proven, this would hint that nature evolved ways to protect and exploit quantum effects right inside living cells. Photosynthesis, quantum coherence, and energy transfer plants are masters of efficiency, especially when it comes to photosynthesis, the process of turning sunlight into chemical energy. At the quantum level, the energy absorbed by chlorophyll molecules doesn't simply hop randomly through the photosynthetic machinery. Instead, measurements suggest it may exploit quantum coherence where energy simultaneously explores many possible paths. Much like a wave spreading through a maze, this means plants may effectively sample all routes at once and pick the most efficient path. The result? Near-perfect energy transfer, despite the messy, warm environment. This has fascinated researchers because it indicates that quantum effects can survive in biological systems longer than expected and may provide evolutionary advantages by optimizing energy use. The aroma of quantum tunneling, smell and vibrations. How do we really smell? The common idea is shape-based. Odor molecules fit into receptors in your nose, like keys fitting locks. But that theory struggles to explain some puzzles. Why molecules with similar shapes smell differently? Or why very different molecules smell the same. One intriguing alternative is the vibrational theory of olfactory. It suggests that smell detectors don't only sample shape, but detect how molecules vibrate. The proposed mechanism involves quantum tunneling. Electrons in the receptor might tunnel through the odor molecule, with the tunneling probability affected by the molecule's vibrational frequencies. The brain then interprets these signals as particular smells. While still debated, behavioral experiments in humans and even fruit flies provide hints that vibrational components could contribute to olfactory perception. The promise and mystery of quantum biology is still in its infancy. Much of it involves bold hypotheses, preliminary results, and more questions than answers. But it has opened a new window on life's complexity, suggesting that evolution might have co-opted quantum effects precisely because they offer advantages: better sensing, efficient energy use, or new kinds of biological information processing. If nature can master quantum tricks in the noisy, warm environment of cells, we might learn to do the same in our own technology, bridging the worlds from quantum to classical life. The same strange principles that govern electrons and photons also shape the molecules, proteins, and cells that make us who we are. But how? Why doesn't all this quantum weirdness turn life sloppy and unpredictable? A key part of the answer lies in decoherence. Quantum states quickly lose their bizarre superpositions when exposed to the environment. Living organisms rely on a delicate balance, protecting certain quantum effects long enough to be useful, while maintaining classical stability needed for robust function. Modern research into this balance promises not only deeper understanding of life itself, but new paths for bio-inspired quantum technologies. A new dawn in understanding life instead of viewing quantum mechanics and biology as separate realms. A more integrated picture is emerging. Life is not just chemical reactions in a beaker. It may be quantum computation, entanglement, and coherence playing out in cells. This challenges us to rethink the boundaries between physics and biology, and promises a future where the weirdness of the quantum world is not an obstacle but a bridge, linking the fundamental laws of the universe to the complexity of living things. So, as we explore the quantum mysteries of atoms, particles, and photons, it's worth remembering that those same mysteries might underlie the songs of birds, the green glow of leaves, and even the scents that dance on the breeze. Quantum physics, once thought to be the science of the very small, might just be the science of life. We've journeyed through the mysteries of quantum physics, particles that exist as waves, superpositions that hold multiple realities at once, an entanglement that connects particles across vast distances. This is the heart of the quantum realm, a place where uncertainty and possibility rule. But then, there's the world we experience every day, solid, definite, predictable. A coffee mug is never both here and there at once. Your cat is either alive or dead, not both. Why? The fuzzy, shimmering quantum world condense into the sharp, discrete classical world we see. The answer lies in a subtle, quiet process called decoherence. The vanishing act of quantum weirdness. Imagine a single electron existing in a superposition, its wave function spreading across many possible locations, left completely alone, isolated. From the environment, it maintains this delicate state. But in the real world, isolation is almost impossible. Surrounding us is a noisy environment full of air molecules, photons, vibrations, and temperature fluctuations. Each interaction with this environment gently watches the electron. It doesn't necessarily collapse the wave function in the mystical sense, but it does entangle the electron's state with countless particles in the environment. This entanglement scrambles the electron's coherent superposition so thoroughly that it can no longer produce interference effects, the hallmark of quantum behavior. The superposition becomes effectively hidden, decoded, and what remains appears like a classical particle in a definite state. Decoherence, the bridge between worlds. Decoherence doesn't destroy the superposition. Theoretically, the full quantum state of the system plus environment still contains all possibilities. But practically, we lose access to that coherence because it spreads into the vast degrees of freedom of the Suronians. That means for large, complicated objects like cats, coffee mugs, or people, decoherence happens at lightning speed, on timescales far shorter than we can perceive. These objects interact continuously with their environment, so quantum superpositions fade instantly, leaving behind the classical world of facts and firm outcomes. In this way, decoherence explains why macroscopic objects appear classical, why Schrödinger's cat is never both alive and dead in any observable sense, and why quantum weirdness remains confined to the microscopic, a gentle erosion, not a sharp snap. Decoherence is not a violent, dramatic instant of collapse. It's a gentle, gradual erosion of quantum coherence caused by environmental entanglement. One way to picture it is like the surface of a frozen lake. Beneath lie shifting quantum waters, but the ice above is solid, stable, and reliable. Decoherence is the process that turns the liquid quantum haze into the solid classical ice we walk upon. The role of decoherence in quantum technology is both a blessing and a curse for quantum technologies. For conventional macroscopic systems, it's what creates the classical stability we rely on. For quantum computers and other quantum devices, decoherence is the enemy, constantly threatening to wipe out the fragile superpositions and entanglements that give quantum technology its power. Quantum engineers spend immense effort isolating qubits, the quantum bits, from environmental noise, cooling systems to near absolute zero, and designing error-correcting schemes to preserve coherence as long as possible. Without this battle against decoherence, the dream of powerful quantum computers would fade. Decoherence and the measurement problem. Decoherence plays a crucial role in the long-standing measurement problem of quantum mechanics, explaining why measurements yield definite outcomes despite underlying superpositions, while decoherence shows how superpositions become inaccessible and why macroscopic objects appear classical. It doesn't fully explain exactly how and why a particular result is realized in each measurement. Different interpretations of quantum mechanics wrestle with this ambiguity in varied ways. But decoherence provides the mathematical and physical underpinning for understanding the transition from quantum potential to classical actuality. From maybe to yes, the classical world emerges thanks to decoherence. The murky sea of possibilities that rules the microworld gradually crystallizes into a firm landscape of definite outcomes at macroscopic scales. That it tells us that the classical world is not separate from quantum physics. It's a natural, inevitable, emergent property of quantum systems interacting with their environments. So the next time you pick up a cup or watch the sky, remember, beneath the surface, the universe is still humming with quantum rhythms, but decoherence has gently locked much of that mystery away, letting us enjoy a world that feels solid, reliable, and real. As you settle deeper into your quiet space, tucked softly under your blanket or nestled in a comfortable chair, let your mind gently float alongside the delicate rhythm of the quantum world we've been exploring. In the last chapter, we saw how decoherence weaves a subtle veil between the shimmering quantum realm and the familiar certainty of the classical one. It's like the universe quietly frosting over fragile ripples with a layer of ice, allowing stability and predictability to emerge. But the quantum story does not end there. Just as night folds unexpected shadows within its calm, the mysteries of quantum physics hold even more strange and beautiful surprises, tales where time itself seems to bend and twist, and reality dances like a whisper caught between moments. Tonight, we will breathe slowly into those whispers, into the wondrous experiments called the delayed choice and the quantum eraser, gentle explorations that invite us to relax our grip on cause and effect, time and observation, and remind us that the universe is more poetic than we dare imagine. Imagine a simple table and two tiny slits. Picture, again, a humble table, upon which rests a flashlight. In front of the beam, a simple cardboard sheet with two tiny slits, like little doorways. Beyond it, a screen awaits, ready to catch the light or the particles passing through. When we shine light through those two slits and do not attempt to watch its path, it creates a pattern of bright and dark bands on the screen, an interference pattern, as if each photon, each tiny particle of light, flows like a wave, passing through both slits at once and overlapping with itself. It's a quiet miracle of nature, as if the photon gently hums a song through both paths at the same time, a serenade of possibility. But when detectors peek at the slits, trying to catch the photons in the act, everything changes. The delicate interference fades away. The photons behave like tidy little marbles, passing through one slit or the other, landing firmly in classical clusters on the screen. The universe seems to straighten, taking a breath and settling into definite stories. Now, what if we waited? Here, the universe beckons us to play a new game. What if, just what if, we set up the experiment, but waited to decide whether or not to observe which slit the particle passes through? Imagine letting the photon travel through the slits first, then after it's long gone, choosing to either peek at its path or to leave it unobserved. This is the essence of the delayed choice experiment, a gentle dance with time, where our future decision seems to reach back and influence what the particle did in the past. What astonishing result comes from this seemingly impossible arrangement? Whether or not we choose to observe later, the pattern recorded will match that choice. If we decide to look, the photon behaves like a particle, no interference. If not, the wave-like interference emerges. Even though the photon already passed through, it's as if time is not a rigid arrow but a flowing river, bending to our gaze, inviting us to see that the past is not quite fixed until the present catches. The quantum eraser, a story of forgetting and remembering. Delaying our choice is just the beginning. The quantum world loves a second act. Enter the quantum eraser. Imagine this. The photons carry little marks, subtle hints or breadcrumbs that tell us which slit they passed through. These marks are enough to destroy the interference pattern. But suppose, after the photons are detected and recorded, we cleverly erase those marks, removing all information about their path. What happens then? The interference pattern reappears, as if the photons never revealed their secret. This amazing result reveals that what truly matters is the availability of information, not physical disturbance or any mystical observer effect. The universe treats knowledge delicately, folding and unfolding possibilities depending on what can be known or forgotten. It's as though reality itself pauses until its story can be told. And in the quiet space between knowing and forgetting, the universe hums its softest tune, a gentle invitation to reimagine time. Both the delayed choice and quantum eraser experiments invite us to gently reconsider what we mean by time. Our everyday experience guides us to think of time as a steady march forward, cause happens first, effect follows. But on the quantum stage, things are subtler. Cause and effect become threads woven into a fabric where the past, present, and future are intertwined in a tapestry that resists simple unraveling. No, time does not unravel into chaos or confusion. Instead, it reveals its elegant complexity, a dance of correlations and possibilities where what happens here and now is connected profoundly with what came before and what will come after. It's a reminder that our classical intuition, forged by macroscopic experiences, is a cozy blanket, warm and protective, but not the whole story. Quiet contemplation on reality and observation as you lie still, breathing softly and letting the day's thoughts melt away. Consider how the act of observation in the quantum realm is much more than simply looking or measuring. It is a delicate interaction, a gentle request that reality answer a question, not just a casual glance, but a profound moment where possibility crystallizes into fact. Yet, experiments like the quantum eraser whisper to us that this crystallization is not cruel or absolute, but fluid. It depends on the very information we hold, on what is remembered or forgotten, on how the story unfolds. Perhaps the universe is not a cold clockwork, but a tender storyteller, weaving narratives that shift and shiver until the final page is read. The mystery that comforts and quietly inspires quantum physics may unsettle, may challenge our deepest assumptions about the world, but it also offers a strange comfort that reality is not rigid, not predetermined in the harshest sense. There is room for softness, for possibility. 4 layers of existence coexisting quietly until gently unfurled. It is an invitation to accept uncertainty, not as flaw or failure, but as part of the fabric of the cosmos, a feature woven through the very atoms and light that compose us. Returning to rest, wrapped in wonder so as you prepare to close your eyes, embracing the stillness and inviting sleep to carry you away. Rest in the idea that you, like the particles and waves, the photons and electrons, are part of this wondrous dance, where time sways like gentle waves, where reality blooms softly with each observed moment, and where the universe waits patiently for us to unfold its shimmering story. Let these thoughts cradle you, soft and slow, into a night filled with peaceful dreams. Good night. From the quantum realm, thank you for lending your mind and your quiet curiosity to this gentle exploration. The quantum universe is strange, yes, but also deeply poetic, a place where even time can whisper secrets we are only beginning to hear. Sleep well, knowing that beneath the measured certainty of the waking world lies a softer, mysterious heartbeat, waiting, shimmering, dancing, and when you wake, the universe will still be dreaming too. Good night.